Now we move on to the proof of the existence. Notice that the moreover part, in particular the properties 1, 2, and 3, already give us lots of hints on how to construct this pi, this representation. So, to prove the existence, we will define pi from little SL to C to endomorphisms on V, where V is the span of vectors V0 through Vn by taking pi of h applied to Vi. We define this to be n minus 2i scalar multiple of Vi, and Ve applied to Vi times n minus I plus 1 applied to Vi minus 1, and pi of f applied to Vi plus 1. Of course, we have the conventions as 0. V negative 1 is 0, and Vn plus 1 is 0. Because H, E, and F span SL2C, and V sub i's span V, so we can extend pi linearly to the whole SL2C. But there's one more thing to check. Remember, for pi to be a Lie algebra representation, we need to show that pi is a Lie algebra homomorphism. So it remains for us to check that pi preserves the Lie brackets. Because of the bilinearity of Lie brackets, it suffices to check that pi preserves the Lie brackets on H, E, and F. So we compute first pi of H bracket E applied to V sub I. This is pi of 2E applied to V sub I, which is, by our definition, 2i times n minus I plus 1 applied to Vi minus 1. On the other hand, so look at pi of h composed with pi of E minus pi of E composed with pi of h applied to V sub I. And you compute this. And you pull out those coefficients and use these definitions again. So now you get two coefficients for just V sub I minus 1. And you add them up and simplify it. In the end, this gives you the thing that coincides with this. And this verifies this, that pi of h Lie bracket E is equal to pi of h composed pi of E minus pi of E composed with pi of h. So pi preserves this particular Lie bracket. Now we're going to check the other two Lie brackets. I suggest you to pause this video and compute it on your own, but I will give you the details anyway. So here are the computation details. So we have verified that pi preserves H Lie bracket F and pi preserves E Lie bracket F. So since little SL2C is spanned by H, E, and F by the linearity, pi preserves the Lie bracket on SL2C. And now it remains to show that pi is irreducible. To this end, let U be a non-zero invariant subspace of V. Of course, invariant under pi. And we will show that U has to be V, which is the irreducibility of pi. The idea of the proof is the following. First, we prove this claim. We claim that at least one of the vectors v0, v1 through vn is contained in U. We prove this. We will prove this by using the diagonalization of pi of h, using this number 1 in our definition of pi. Once we have verified this claim, once we have shown that at least one of these vectors, these n+1 vectors, is contained in U, we're going to use number 2 and number 3, the pull back and push forward of vectors, to show that everybody here is contained in U, which forces U to be equal to V. So that is the idea of the proof. Now let's prove this claim. Indeed, since pi of h applied to U is contained in U, because U is pi invariant, pi of h restricted to U as a complex linear operator on the vector space U must have at least one eigenvalue and eigenvector. This is because U is non-zero, so its dimension is at least 1, and because C, the field of complex numbers, is algebraically closed, so there must exist at least one eigenvalue, and there's a corresponding eigenvector. Say pi of h applied to U is lambda U times U, where lambda U is a complex number and U is a non-zero vector in U. But remember, from the definition, pi of h applied to vi equal to n minus 2i applied to vi, where I is 0, 1 through n. This is our definition for pi of h, which means the n plus 1 values, negative n, negative n minus 2, all the way to positive n minus 2, n, are all possible eigenvalues of pi of h. These are the only possible eigenvalues for pi of h. Because pi is always non-zero vector for I equal to 0, 1 through n. What does this tell you? This tells you that even if you restrict pi of h to u, you cannot have any eigenvalues other than those n plus 1 values. So this tells you lambda sub u must be one of them. Now if lambda sub u is n minus 2 times I sub u for some I sub u from 0 to n, then u above this vector u must be a non-zero multiple of v sub iu. Because this is the eigenvector corresponding to this eigenvalue. This is because the eigenspace for the eigenvalue lambda u, which is n minus 2iu, can only be one-dimensional. To say this in another language, which might be more familiar to some of you, we can also say that pi of h is diagonalized by the basis v0 through vn. That we have n plus 1 different eigenvalues gives us that the corresponding eigenvectors must be linearly independent. It follows that this ditto v sub I sub u as a multiple, as a non-zero multiple of u, must also be in the vector space u. And this verifies our claim here, that at least one of those n plus 1 vectors is contained in u. Now we can finish the proof. Now suppose, for convenience, bk is in u. You can just take this k to be this I sub u. But we use k here just to simplify our notation, where k is 0, 1, or n. Then by applying pi of e for k times, Now recall our formula, our definition for pi of e. Pi of e is defined to be pi of e applied to vi equal to this scalar multiple of v sub I minus 1. Since u is pi invariant, we have, after applying this for k times, the v naught must be in u. We get the first vector in the basis v naught v1 through vn that lives in u. So this is a pullback process. We can also push forward by applying pi of f. Now applying pi of f, noticing that u is pi of f invariant. U is pi invariant. Gives us, so here we recall our definition of pi of f applied to vi, which is simply vi plus 1. This gives us everybody is in U. But those vectors precisely span V. So we have U is equal to V. And we are done with the proof of the existence. And that's the whole proof.